Okay, continuing on in Chapter 3, we are in Section 3.2. We're talking about the slope of a line. So we introduced linear equations in the last section, and we graphed a couple, and we talked about what we need to graph them. Remember, just to remind you, that's minimum of 2 points. Intercepts are a good choice because they're easy to find, setting x equals 0, y equals 0. In this, we're going to dive in a little bit more into the nitty-gritty of these lines. So we're going to talk about how to find the slope of a line. And then we're going to look at slopes of horizontal and vertical lines. And then we're going to talk about two types of special lines. Those are parallel, two classes of special lines, parallel lines and perpendicular lines. So let's jump in with slope. Our definition here, the slope of a line is the rate of change of that line. So underline that. It's between 2 points on a line. So it's how fast your line is changing from one point to the next. Slope is the same regardless of the points. That's supposed to be of the points used to calculate. So if you use any 2 points, you'll get the same slope. It does not matter. This is unique to what linear equations are. So to find a slope, we need a slope formula. So given a line L, and we have 2 points that L passes through, A, B, and C, D, because remember, it does not matter what 2 points we have, then we can calculate the slope by calculating the change in y divided by the change in x. And a lot of times we learn this as rise over run, or mathematically, we usually denote this as delta y over delta x. This little triangle is the lowercase, is it lowercase? No, it's capital delta from Greek, ancient Greek. And delta literally means change. So this is change of y over change of x, exactly what we have written in words here. And with these 2 points, that means it's d minus b over c minus a, as long as c does not equal a. Now there is something important about this calculation. It doesn't matter which point you pick to go first. I chose C and D, but you can remember this easily by whatever point is here, whatever component of the point you're using here, the matching or the corresponding component needs to be down here. So if I did B minus D, this would need to be A minus C. It doesn't matter what order you do it in. It does matter that up and down on your slope calculation corresponds to the same point. So let's do a couple calculations. We're going to calculate the slope of the lines that go through these points. So we're going to start with A. So we have 2, -1, and 0, 5. So just to kind of showcase what I was talking about here, this format says I should do 5 minus a -1 divided by 0 minus 2. And that's going to give us 5 plus 1 is 6 over -2 equals -3. So just for fun, let's calculate it the other way. Let's say we did the first one first. -1 minus 5. Now since I chose -1, on the bottom it needs to be 2 minus 0. Well, -1 minus 5 is -6. Divided by +2 gets us -3. So it doesn't matter what order we set up our points as long as up and down the components match. So let's take a look at B here. We have -3, 5, and -2, 0. So I'm going to do 5 minus 0 over -3 minus a -2. 5 minus 0 is 5. -3 plus 2 minus negative makes it plus. It's -1. And so this slope is -5. And then for part C here, we have -1/2 comma -4 and 1.5 comma 1.5. So we have 1.5 minus a -4 over 1.5 minus, now I'm going to write 1/2 as -0.5 in decimal since I have decimals. This is 5.5 on top. 1.5 plus 0.5, because these get switched to pluses, is 2. And 5.5 divided by 2, 5.5, if I write it as a fraction, is 11/2. 11 over 2 over 2, which gives us 11/4. So those are our slopes. You have some practice ones here to give it a whirl. So moving on here, we're expanding our definition of lines. So we've seen standard form, ax plus by equals c. So to find slope from standard form, because we don't have to switch it, we don't have to do anything to it, we just know that our slope is -a over b. So that's how you find slope out of standard form. And we also saw in the last section, slope-intercept form is y equals mx plus b. Now this is the preferred version for a lot of students of lines, because m is our m for slope, and b, if we put it into a point as 0 comma b, is the y-intercept. So it literally gives us slope and the intercept, the y-intercept. Again, mathematicians are lazy. So you don't need to switch to slope-intercept form every time. Some people don't like it because standard form gives us the slope, -a over b. But if you like slope-intercept form, you can always simplify this, solve it for y, and you'll be right here and get your slope immediately. So if we turn the page over, excuse me, we are going to do a little bit of converting here. So we're going to write the equation in slope-intercept form, and then we'll identify the slope and the y-intercept from that equation. So we're going to subtract 5, subtract 5. We have 3y equals, distribute that 3x plus 6 minus 5. We have 3y equals 3x plus 6 minus 5 is plus 1. Divide by 3, we get y equals x plus 1/3. And yes, this is the same equation that we graphed before. And our slope then, looking at in this form, our slope is 1, and our y-intercept is 0 comma 1/3. Now, we could have done that from standard form. Now, this isn't quite standard form yet, so if we write it as standard form, it's 3y plus 5 equals 3x plus 6, and we would need to subtract the 3x over, and we'd have -3x plus 3y, and subtract the 5 over, equals 1. So standard form says it's -3 over 3, which is 1. And so our slopes match, and our y-intercept we would find by setting x equal to 0 and solving for y. So we have a practice problem for you to try, just converting from standard form into y-intercept, and I recommend you simplify this out and write it as standard form and make sure that they match to check your work. But now we're going to move on here, and your version should be correct. I had the wrong setup for this problem, but we are going to write in slope-intercept form and then graph it, not just find the intercepts. We did that last time with this exact equation. So, writing in slope-intercept form, we are going to subtract the 3x over, so we'll have 4y equals -3x minus 12. Divide everything by 4. We have y equals -3 over 4x minus 3. And so our slope m is -3 over 4, and this is where we're going to think of it as rise over run. and our y-intercept is 0, -3. Now the other reason people tend to like slope-intercept form, give ourselves some axes here. Now, why am I giving myself axes built like this? Because I'm going to start with 0, -3. 4, 5, 6. So -2, -4, -6. 1, 2, 3, 4, 5, 2, and 4. And we'll go one more to 6. So, as I was saying, the other reason why people tend to like slope-intercept form is because we can now graph this line without having to graph more than one point. So I'll do this in a different color so it stands out a little bit more. But we plot 0, -3. And then we use our slope, our rise, and our run. So our rise is -3, which means we drop down 3 to -6. And we run over +4 to here. And this is 4, -6. And then now we have our 2 points. Connect the dots and we have our graph. This is y equals -3/4 x minus 3, not 12. Oops, make a real big 3 there. So yes, we graphed this using intercepts before, and if we extended this out, this would be -4, 0. This is just another way to handle graphing linear equations. If you have your slope and you have your y-intercept, you have all you need, because you can build out the second point you need by going down 1, 2, 3, and over 1, 2, 3, 4. So this is -3 and 4. Okay. So just another way to graph some equations. So in these last 2 examples here, we're going to identify the slopes of the following lines. So if you're paying attention closely here, or doing these one after another, you'll notice that these are the graphs, the equations, the lines that I asked you to graph in the last practice problem of 3.1 and to describe it. So we're going to start this one and come back to it in a second. And we're going to look at B first over here. So if y equals -3, we can write this as y equals 0x minus 3, because 0x is 0. So that means our slope, m, is 0. The other way we can think of this is if we set up our slope calculation, we always have -3, and then we have x2 minus x1, whatever those components are. We don't actually need to care about what they are, because -3 plus 3 is 0 over x2 minus x1, which is still 0. So 2 ways to think about it: slope-intercept form or a straight slope calculation. In either case, we get 0. And so it's 0 slope because there is no change in y. So if you've done the practice problem, you know what kind of line this is. This is a horizontal line. Now, if we come back to A is a bit different because we're missing the y, so we can't look at a slope-intercept form. But we can do a slope calculation. So we have y2 minus y1 over 2 minus 2. And that's going to be y2 minus y1 over 0. Well, this is bad, because as we know, 0 is the only number we're not allowed to divide by. So this is undefined. And again, if you've done your practice problems, you know that this is a vertical line. So just to kind of codify what we're saying in these examples in the next definition box here, the slope of any vertical line, which always has the form x equals a, is undefined. And the slope of any horizontal line, which always has the form y equals b, is 0. And this doesn't matter which horizontal or vertical line we're talking about, they always have these slopes, and they always look like this. So vertical lines are x equals a number, horizontal lines are y equals a number. Now for parallel and perpendicular lines, you're going to have some homework problems on them. They're very simple. Once you see the definition, they make a lot of sense. So for parallel lines, two lines are parallel if and only if they have the same slope. So if the slope of one line is 2 and the slope of another line is also 2, they will be parallel. And that makes it really easy to find parallel lines because you just pick any other line that goes through a particular point and has the same slope. Perpendicular lines, a little bit different. So for parallel lines, we're thinking they do this. They run parallel like train tracks. For perpendicular lines, they go like this and make a 90-degree angle. So that's a little bit special. So two lines are perpendicular if and only if they have opposite and reciprocal slopes. So if m is the slope of a line, then any perpendicular line must have slope of -1 over m. So much more unique. So if you have your slope m, you make it negative, you switch the sign, and you divide it. You put it on the bottom of a fraction, divide 1 by that number. And that gives us this nice perpendicular line. Now, you can have lines, this is one example here, but you can have perpendicular lines like this too, where they intersect way over there. That depends on what point that you're looking at. So that is the end of 3.2. Got a little bit of practice and some homework to go with these.